Now we're thinking about something closely related to electric force, electric field. Uh, they're closely related, but they're not the same, and they both start with the same letter, so it's easy to get them confused. But try not to get them mixed up. Let's think about it this way. Imagine some region of space that has a whole bunch of electric charges in it, and then into that space wanders some other charge. We'll say it's positive. The book calls this a probe charge because as this charge wanders into this area, it feels electric forces, a different electric force depending on where it's located. And let's say this charge, positive charge Q, lands at some point X, and of course it'll feel force. It'll feel a net force from all the other charged particles. And we think of that force this way. The force on charge Q when it's sitting at point X is equal to the charge times something that was already there at point X before the charge Q got there. And that thing that was already there at X is called electric field. The idea is that the space between those charged particles isn't empty space. There's something there in the space between, and it's electric field. We think of it this way, that any charged particle does something to the space around it, fills that space with electric field. And then when another charged particle comes into that region that has electric field, it actually feels the electric field. It is literally in contact with the electric field at this point. And that's how it feels the force, by being in contact with the field at that point. Here's the basic relationship between field and force. Or we could write that equation a little bit differently in a way that serves as a definition of electric field. Right? The electric field at any point, like call it X, is equal to force, the force that you would get if you put a charged particle at X, divided by that charge. And we'll think a lot more about what that definition means. But it's important to realize that you don't have to actually have a particle at point X in order to have electric field at X. You just need other charges somewhere near X. And then in all the space around those charges, including point X, there will be electric field. Now, we started by assuming that this charge is positive. So now look at this equation and think about the direction, or we can indicate direction with sign, the direction or the sign of the force and the field. Well, this is a positive number, which means the sign of field will be the same as the sign of the force caused by that field. Or to put it another way, the direction of the electric field will be the same as the direction of the force, because the sign of the field is the same as the sign of the force, and they are the same because this charge was positive. So there's our interpretation for the direction of a field. Right? Field is a vector, so it's got a direction as well as a magnitude. And here's the slogan: the direction of electric field is the direction of the force on a positive charge. Or to put it another way, at the direction of the field at any point near the charge that is causing electric field. The direction of the field at any point is the direction of the force that a positive charge would feel if it were at that point. For example, let's say we have just one little lump of positive charge. What's the direction of the electric field at that point? Well, the direction of the electric field there is the direction of the force that a positive charge would feel if you put a positive charge here. And of course, if you put a positive charge here, it feels a repelling force from this other positive charge. So the force on a positive charge located here would point straight directly away from this charge. And since that's the direction of the force that a positive charge here would feel, that's the direction of the electric field at this point. And similarly, if we look at this point, imagine putting a positive charge there. It would feel a repelling force from this, so it would feel a force in this direction. Since that's the direction of the force that a positive charge would feel if a positive charge were sitting here, that's the direction of the electric field. And similarly, if you had, instead of a positive charge here, you had a negative charge, what's the direction of the electric field at that point? Again, imagine putting a positive charge there. What kind of force would it feel? Well, positive charge here, there's a negative charge here, so there are attracting forces. This positive charge is attracted, it's pulled towards the negative charge, so the direction of the force on a positive charge, if you put a positive charge there, is this way, so that's the direction of the field at this point. And the direction of the field at that point, same deal. Imagine putting a positive charge at that point. What kind of force would it feel? It would feel an attracting force from this negative charge that was there already. So in other words, it would feel a force in this direction. Since that's the direction of the force that a positive charge would feel if you put a positive charge here, then that is the direction of the electric field at that point. Okay, so much for direction of electric field. What about magnitude of electric field? That depends on what kind of charge or charges are actually producing that field in the space around the charges. Let's just look at the simplest example. An electric field that's caused by just one charged particle, just one lump of charge, one proton in a hydrogen nucleus, something like that. So Q is the charge that is causing there to be electric field in the space around Q. Whenever I'm talking about a source of some kind of electric field, I'll always indicate that with a capital Q. And then when we think about some other charge that comes into that region and feels the field that was caused by capital Q, that charge that's feeling the field, I'll always indicate that with a lowercase q. So imagine lowercase q, and we're still thinking of it as positive, comes into this region and lands right here. So what then is the magnitude of the electric field at point X? Go back to our version of the equation, the version that serves as a definition of electric field, and that's just the going to be the magnitude of the force on that positive charge when it's sitting at point X, divided by the actual numerical value of that charge. Well, we know what the force on one charge is when it's a force coming from one other charge. We just use Coulomb's law, the basic rule for electric force. And then this equation will look like this. Magnitude of that force is just the K constant times the magnitude of the charges, the magnitude of the charge that the force is coming from, the source of the field, the source of the force, times the magnitude of the charge that is feeling the field and feeling the force, divided by square of the distance between capital Q and lowercase q. That distance d is this distance here. And so that's the numerator of this equation. The denominator is just plain Q, the charge that is coming into the picture and feeling the field that was already there at point X. Since Q is positive, then the absolute value of Q is the same as Q itself, because Q is positive. So that gets canceled out by that. And all we're left with for the magnitude of the electric field at point X, which is a distance d away from the source charge, is just K times the magnitude of the source charge divided by the square of the distance from the source charge to point X. Notice that this has the same relationship with distance as electric force had, not surprising. And whatever, all the things that we said about force, we can say about electric field as well. For example, if you double the distance, you cut the magnitude down to 1/4 of what it had been before. Let's look at an example of that. Let's say we've got a positive charge here, and then no charge there, but we're just going to be thinking about the net electric field at this point. So that's a distance d away from the positive charge, and then also a distance d away from that charge is a negative charge. So then the field at X is a net field. It's the sum of the field from the 1 unit of positive charge plus the field from the 1 unit of negative charge. And when we're thinking about this algebraically, we'll do the same thing that we did with forces. Anytime you have 1 unit of charge causing an electric field 1 step away, we'll just say that the magnitude of that field 1 step away is plain old E. So in this case, the field from the positive charge is a field caused by 1 unit of charge 1 step away, so the magnitude is E. And what's the direction of the field at X caused by that charge? Well, do the same thing. Imagine what would happen if there were a positive charge at point X. imagine putting a positive charge there, it would feel a repelling force from this. A positive charge here would feel a force pushing to the right. And we'll say right is the positive direction. So that is a field of plus E. And then the other field comes from this. And again, this is one unit of charge causing a field one step away. So the magnitude of the field at X that is caused by this is also just plain E. And then what's the direction of that field? Well, put a positive charge there and then ask what kind of force would it feel if you put a positive charge there. It feels an attraction from this. It feels a force pulling it to the right. Positive charge is attracted to this negative charge, so it feels a force in the positive direction. So that's the direction of the force on a positive charge, force coming from this thing. So that's the direction of field at this point, caused by this thing. So then the net electric field at that point is twice as strong as the field we would get from just one charge, either the left-hand charge or the right-hand charge. Now let's flip this around just a little bit. Positive charge here, negative charge here, one step away. And then one step away from the negative charge is the point X, and we'll now again think about the net field at X. And again, the field at X is a net field, the sum of the field from the positive charge plus the field from the negative charge. So first, the field from this one, imagine putting a positive charge here. There's positive charge here as well, so there's a repelling force from this on a positive charge here. A positive charge here is pushed away from this positive charge. So a positive charge here feels a rightward force from this, force in the positive direction. And what is the strength? What is the magnitude of that field, of the field at this point caused by this? Well, now you don't have one unit of charge causing a field one step away. You have doubled the distance. And when you double the distance, you cut the strength down to 1/4. Whether you're talking about the strength of the force or the strength of a field, you cut it down to 1/4. So, in other words, the field caused by one unit of charge one step away is just plain E. The field caused by one unit of charge twice as far away is 1/4 of that. And then the other contribution to the net electric field here is the field caused by this. And this is one unit of charge causing a field here that's one step away. So the magnitude of the field caused by this one, field at this point, caused by the negative charge, the magnitude of that is just plain E. And is it positive or negative? Well, imagine putting a positive charge there. It feels an attracting force from this one. A positive charge will be pulled to the left by the force that comes from this one. So left is the direction of the force on a positive charge at this point. So left is the direction of the electric field at this point, the electric field caused by this. So we have that, and then that means the net electric field at point X is minus 3/4 times E. Now, one more with just a very slight change. Let's take this same setup here. And now double the charge on the far away one. It's now 2 units of charge. So doubling the charge means that the force felt by a positive charge here would now be twice as strong. Remember the basic rule, Coulomb's law. Where this is the absolute value, the magnitude of the charge that is the source. If we imagine putting a positive charge here and asking what kind of forces it feels, this charge is a source of a force on a positive charge if you put a positive charge here. But between the last example and this one, we have doubled the charge. In other words, we double this factor. Everything else is the same as it was in the previous example, which means we have doubled the strength of the force. That doubles the strength of the field, because magnitude of the field is just equal to magnitude of the force divided by Q, the probe charge, the thing that is feeling forces and fields. And in the case of a field caused by just 1 unit of charge, it's K magnitude of the source charge over d squared. We just doubled that, left distances the same, so we've doubled the strength of the field. Previously, the strength of the field here that's caused by this was 1/4 E, but now we double the strength of that field by doubling the charge, so now it's 1/4 times 2 E, or 1/2 E. And it's still a force in the positive, a field in the positive direction, because you put a positive charge here, it'll feel a repelling force, a force in the positive direction coming from this. And then we did nothing to change this. It's still 1 unit of charge causing some field here at a point 1 step away. So the magnitude of the field that this thing causes at x is again E, and it's a field pointing in the negative direction, because if you put a positive charge there, it'll feel a leftward attracting force from this. So now the net charge at E is a little bit different, smaller in magnitude. Now it's just minus E over 2. Previously it was minus 3/4 E. And then we'll practice some more of this in